Hi, I'm Norman Wildberger. We have now finished part 1 of this video series on hyperbolic geometry. In part 1 we introduced the general framework for the subject and in some detail built up the main laws of trigonometry for this universal hyperbolic geometry. Now we're in a great position to carry on and prove a lot more interesting things in that direction, but what we're going to do now in this second part is something somewhat different. I want to enlarge our scope considerably by positioning the universal geometry that we've learned in the hyperbolic setting so far inside a larger arena of adjacent connected geometries. So I want to show you that there's a lot of interconnections between not just hyperbolic geometry, but also Euclidean geometry, elliptic geometry, spherical geometries, affine geometry, relativistic geometry, inversive geometry, vector geometry or linear algebra, projective geometry. So the aim of this part 2 is to bring geometries together. In particular, we're going to be interested in the relationships between hyperbolic geometry and elliptic geometry to begin with. That's going to be a very interesting development because elliptic geometry, or the closely related spherical geometry, is a subject that goes back to antiquity. And with our algebraic point of view, we are going to be able to restructure that subject. So we're going to have another look at spherical geometry, the same spherical geometry used by astronomers, used in geodesy, just concerned with the structure of the sphere. And we're going to be seeing that and looking at it in a new light from this point of view coming from the hyperbolic geometry that we've already talked about. Remarkably, we're going to find out that elliptic geometry and hyperbolic geometry essentially share the same main laws. This is a vitally important and remarkable aspect of this approach. So all the theorems pretty well that you have already learnt and the formulas that you have become familiar with in part 1 are going to be applying not just to hyperbolic geometry but also to elliptic geometry. And so they have direct applications to spherical geometry, to the geometry of the earth in which we live in, to the sky in which we find ourselves. But I want to do more than that. I also want to connect these geometries with these other geometries. There's all kinds of interesting connections. And so what I want to do is sort of position geometry to create a larger framework in which we can view a lot of different geometries kind of simultaneously, especially interested in the connections between them. Because of this very general aspect, or this general approach that I'm going to be taking, I'm going to, at least at first, be somewhat descriptive. We're not immediately going to get into formulas and precise formulations. We may have to put that off for a while. So our first order of business is just to get us familiar with some of these geometries and basic aspects of how they fit together. So in the first couple of lectures in this new part 2, I'm going to give an introduction to spherical and elliptic geometries. And we're going to go back quite some ways into first historically, but also in terms of the level of which we're going to be talking about. So a lot of the things I'm going to be mentioning in these first few videos will be pretty obvious if you had some geometry, relatively elementary, basic definitions, or an initial orientation to the study of essentially the sphere. The sphere is arguably the most studied geometric object from a historical point of view. The sphere has fascinated mankind for a long time, and with good reason. And the ancient astronomers particularly were fascinated with spherical geometry. because of the relatively obvious observational fact that the sky above us looks like a sphere. So the celestial sky looks like a sphere because when we watch it over a night or over many nights, we see that it revolves and stars come up and then they go down. The sun comes up and then goes down. The moon comes up and goes down. We can see by watching the stars that the whole thing is rotating around. And if we're living in the northern hemisphere at some latitude, then we can actually quite easily see where the center of this rotation more or less is. A certain direction in which everything seems to be revolving around that direction. So it's hard to avoid the idea that we're living in some kind of bubble with a big sphere around us, and on this big bubble, this big sphere, there are all these little points of lights which we call stars, and there is also the moon and the sun and the various planets which sort of are associated to this sphere but sort of move subtly on it. So the geometry of this sphere is really a main motivation for geometry overall, and especially for spherical geometry. And it's maybe a surprise to many students to find that some of the formulas and theorems that they're mostly familiar with in the planar case, in terms of planar Euclidean geometry, were first studied and discovered in the spherical case, which these days is considerably more subtle and a harder, much less well-known studied subject. Other examples of things which are round are the moon, which certainly appears to be round, the sun, and possibly the other planets and stars, although it's not so clear because you can't see them very well. The earth is round, and at some point ancient peoples kind of suspected this, or maybe were quite convinced about it. Not all ancient peoples thought that the earth was flat. In particular, the fact that the sun is coming up in this direction and goes down that direction, and then the next morning it's back where it started, suggests that it's going all the way around us. And that's a little bit hard to imagine if we're just a plane. A lot easier to imagine if we're on a sphere, and then there's some space for the stars and the sun and the moon to go around us and come back up the next day. There are quite a few objects in ordinary life that are round or pretty well round. An eye, a pebble, although it's actually not so easy to find a very circular or spherical pebble, but a snowball, which you can easily make if you're living in snow, a pearl, of course, a berry, an orange, and then with sports, a ball, very familiar object, cannonball, a water drop, and no doubt you can think up many other examples. So here's an example of a sphere. Okay, it's a very beautiful symmetrical object. It's the most symmetrical object, really, and for that reason alone it's fascinated mankind for a long time. And probably in the course of this the development, it's probably good for you to have a sphere at hand that you can look at. The sphere is a rather subtle object, and it's easy to get a little bit confused by it. Having a model of it, having an actual sphere that you can touch, move around, look at, helps a lot, I think, in developing our intuition. So let's start out with our initial orientation of just trying to define some terms and introduce some basic notation and ideas for a sphere. So here's a slightly smaller sphere, at least a bit more manageable, that we're going to be talking about. So first of all, let's give a name for a sphere. Let's call it S typically. There's our representation of a sphere, and this black line here that's solid in the front and dotted at the back represents what you usually call something like an equator. So for example, in this model here, you can see that red line there goes all the way around. If I go all the way around, you can see it joins back up to where it started. All right. And that's That's an equator, and if you're looking at it something like this, you'll see that part of it. You won't see the part that's behind it because the sphere is in the way, but I represent that part or extension of this equator with the dotted lines behind. Now, an important point associated to the sphere, in fact, really the only point that you can associate to a sphere that's canonical and important, is the center. So somewhere right in the middle of the sphere is the center, and we'll usually refer to the center as O. And it's in the middle of the sphere in the sense that all the points on the sphere are equidistant to this center point O. So however you're going to measure the separation of two points, be it with length or with quadrants or with something else, that measurement is going to be the same if you start with the center point O and any point on the sphere. Or another way of putting it, the segment joining the center to any point on the sphere is congruent to any other such segment. Congruent in the sense of we can make a motion that sends one segment to another, preserving then its length or its quadrants or however you're measuring it. So I use the term equidistant here not to imply that we've got a measure of distance, but just that we have some way of measuring the separation between 2 points. Now, an important clarification, the term sphere usually refers only to the surface itself. If we want to talk about the region that's enclosed by the sphere, we usually use the term ball. So the ball refers to the sphere itself and all the points inside, while the sphere just refers to the points on the outside, the ones that I'm able to touch here. In particular, that origin, or that center O, which is inside there, is a little bit hard to get at. From the outside here, right, we have a struggle trying to sort of see where that center is and to talk about it practically. It's a little bit beyond our view. The radius of the sphere is a distance, so it's the distance from the center to any point on it. And then we also have the notion of a diameter, which is twice the radius. That's the distance between a point B and the opposite or antipodal point, which will usually denote B bar. So this is an important construction, that if you start with any point on the sphere and you make a line passing through the center and you come out the other side, then these 2 points are called antipodal. So for example, in this little picture here, now there's a point A, and the point directly opposite it, which is roughly that one there, I've called it A bar. Okay, so this point and this point, they're antipodal. So if we join those 2 points, then the line created would pass through the center. That's a very important property of the sphere, that every point has an antipodal point and vice versa. For example, this point B has B bar here as its antipodal point, and so on. So let's define spherical geometry roughly as the study of points, lines, regions, and so on the surface of a sphere. So we're going to be interested in points, like this one, or this one, or this one. We're going to be interested in lines, for example, something like this, or something like this, or something like this. Regions, like that little triangle. Or maybe more complicated things, maybe circles. Maybe we'll be able to define conics, make measurements, but everything on the surface of the sphere. So even though this is all happening in three-dimensional space, the actual constructions and measurements are taking place purely on the surface of this sphere. So it's necessarily complicated by the fact that the sphere is curved. It's geometrically more subtle than working on a plane. In particular, for example, the question of what do we mean by a line in the first place? Is a line straight? In Euclidean geometry, the notion of a straight line is reasonably clear. What does it mean to be a straight line on a sphere? Well, to answer that, let's go back to our sort of most important straight line, this equator that we've drawn here, how can we characterize that equator as a line on the sphere? Well, you could say, well, if I'm walking on the sphere, that's kind of going in a straight line. That's just proceeding in the direction that we came from, carrying on. But a slightly more manageable definition there is to think in terms of the ambient three-dimensional space and in terms of a plane that cuts the sphere, passes through it, and actually goes through the center of the sphere. So, here, for example, is a plane. And this little cutout is just meant to represent part of the plane. The plane itself is actually meant to extend in all directions. Now, if we imagine this plane as meeting the sphere, then it cuts out this equator. And the crucial property of this plane is that it actually passes through the center of the sphere, as opposed to, say, this one here. That plane does not pass through the center. This one does. And so the line that this cuts out has some special property. In fact, that's what we're going to be calling a line in spherical geometry. So that's the defining property of the equator, and that motivates our notion of a line. So in Euclidean geometry, we naively think of a line as being a shortest path between 2 points. In the circle, we're going to introduce this definition that a great circle, first of all, is the meet of the sphere S and any plane passing through the center O. And so we're going to define a line in spherical geometry to be a great circle. So it's actually a circle all the way around the sphere, like the equator. That's obtained by intersecting the sphere with a plane through the center. And it can be oriented in any direction you want. The plane can be in any direction as long as it passes through the center. Alright, so here's a picture where we have an equator in black. There's the part behind that's behind us. And I've also shown you two other great circles. Here's a great circle in red. That's the part you can see. That's the part that's behind. And here another great circle in green. That's the part you can see. And then that's the part that's behind. So given 3 lines, as in this diagram, we get 6 points of intersection. These 3 lines meet in 6 points. Let's count that. So first we have that, say, initial great circle, that one there. When we introduce a second great circle, say the red one, then we get 2 intersection points. We get the point A pictured here, as well as the antipodal point A bar, which is where the back of the red great circle meets the back of the black red circle. So with 2 lines, we have 2 intersections, and they're antipodal points. If we add now a third line, well, then that third line meets the black line in 2 points, which are antipodal, and it meets the red line in 2 points, which are antipodal. So altogether we get 3 pairs of antipodal points, 6 points altogether. A bar, B bar, and C bar. And these 3 lines, making 6 points, also cut out some objects which we might call triangles, or spherical triangles. And here's one such example. A spherical triangle, and I'll use the notation A, B, C with a bar over it. It's our standard notation for a triangle. So we're talking about this point, and this point. And we can imagine this little region here as being the triangle, if you like. Or if you like, you can prefer just to think of the 3 points, or you can think in terms of the 3 lines, or some combination of those various things. So in our example here, again you can see 3 points, A, B, and C. And there's one triangle. And then there's the antipodal points of these 3, which are on the other side. A bar, B bar, that's supposed to be C bar. And so that's sort of the antipodal triangle to the one that I started with on this side. So all the constructions sort of have an opposite orientation. But it's a little bit interesting and important to observe that this triangle ABC that we start with on this side and the antipodal triangle A bar, B bar, C bar on this side have a little bit of a different aspect. Can you see that the orientation of this one and the orientation of this one are reversed in some sense? Here, if we go from A, B, C, we're kind of going in this direction, which is a clockwise direction. While if we look over here, A bar, B bar, C bar, that direction is an anti-clockwise direction. So the notion of orientation is reversed when we go from an object to its antipodal object. And how many regions are there altogether? There's actually more triangles than just two, because, for example, here's another triangle, and here's another triangle, and here is another triangle. There's another one. There's another one. Maybe it's a little bit challenging to count, but if you stare at this picture here, I hope you'll be able to see that there are 8 triangles. And another way of seeing that is the first line or equator that you draw divides the sphere into 2 regions. And then when you add the second great circle, it cuts each of the existing 2 regions in half. So then we have 4 regions. And then when we add the green line, it's cutting each of the existing regions again into 2. And so we end up with 8 different regions. And they're all triangles, bigger and smaller perhaps, depending on the positions of the 3 lines. A few more useful definitions that are pretty well the same as they are in Euclidean geometry. We can say that 3 lines D, F, and G, say, typically I'll use small letters for lines, that they are concurrent precisely when they pass through a common point, say A. And 3 points, capital A, B, and C, are collinear precisely when they lie on a common line, D. So line here means line in the sense of great circle. So 3 points which lie on a great circle are called collinear. And an official definition of a triangle ABC with a bar over it, where A, B, and C are points, is a set of 3 non-collinear points. And then there's a kind of a dual notion of a trilateral. If we have 3 lines, D, F, and G, and they're non-concurrent, so they don't all pass through the same point, then we can say that that set of 3 lines is a trilateral. Here's a first exercise you might like to think about, which we've already talked a little bit about. How many triangles are formed by a trilateral? And conversely, how many trilaterals are formed by a triangle? While spherical geometry is essentially a 2-dimensional geometry, because the surface of the sphere is essentially 2-dimensional, it nevertheless is living inside this 3-dimensional space. And it's hard to ignore the geometry of the 3-dimensional space when we're talking about spherical geometry. In the 3-dimensional space, we have points and lines as usual, but we also have planes. So we have points, we have lines, and we have planes. So these sort of 3 fundamental linear type objects. And let's introduce just a few ideas and terminologies for points, lines, and planes. First of all, if we have 2 points A and B, then they determine a line which we'll denote by AB. So AB is the line joining A and B. We'll often say the join of A and B. Secondly, any 2 intersecting lines, say L and M, determine a plane, P. So here's a line and here's another line, and if these 2 lines are intersecting, so imagine they actually meet there, then those lines form a plane. Yeah? And if that's a line L and that's a line M, then the intersection of the 2 lines is LM. And we won't quite yet introduce a notation for the plane determined by L and M. Another possibility, if you have two lines, is that they are skew. So two lines in three-dimensional space don't have to meet. In fact, typically they don't. So if we have two lines like this, then they're skew, we say. Just a terminology. And what about two planes? Well, generally if there's one plane and there's another plane, then those two planes are going to meet in a line. That line there. Right? Line of intersection. So in this picture, there's one plane, say R, there's another plane P, and they're meeting along this line, and we'll denote that line in which the planes P and R meet by PR. We also have a notion of parallel lines. So two lines are parallel, means they have the same directions. In this case, they also lie in a plane. So, for example, these two lines are parallel and they meet in a plane. They lie in this common plane. Typically, skew lines do not meet in a plane. You can't form one plane that passes through two skew lines. But if the lines are parallel, you can, or if the lines are actually intersecting, then you can find a plane that passes through them both. We also have a notion of parallel planes. So for example, if that's a plane, and that's a plane, then these two planes are parallel. Okay, even if you extend them, which I always suppose you can do, then they still stay non-intersecting. So we have a notion of parallel lines. We also have a notion of parallel planes. Another interesting idea that will be important for us is the idea of a circle on a sphere. We already talked about a great circle, like the equator, but there are also lesser circles which are not quite as important as the great circles. So a general circle on the sphere is defined to be the meet of the sphere with a general plane P. So if there's a sphere and we look at the intersection of the sphere with any plane, then we're going to get a circle on the sphere. We define that object to be a circle. So here's a picture here, the sphere, the center, a plane P cutting out or intersecting a circle, say C. There's the great circle. That's our usual picture of equator. So the special case when the plane P passes through the center, then a circle is actually a great circle. Now a circle has the property that it divides the sphere into two regions. So if I take a sphere and I take any plane through it, that circle that we get divides the sphere into on one side of the plane and on the other side of the plane. And we have a special term for the half of the sphere that we get when we have a great circle. So in the case of a great circle, the regions on either side are called hemispheres. So for example, the northern hemisphere or the southern hemisphere, if this was a model of the Earth and this was the actual real equator, then the above part would be the northern hemisphere, the bottom would be the southern hemisphere. So if we're on a very big sphere and we're very little creatures making our measurements along here, making lines, triangles, maybe measuring angles, or maybe measuring spreads, measuring distances, or perhaps quadrances, we can think about trying to do essentially Euclidean geometry in this context. If it's a very big sphere, we might not know that we're on a sphere. We might think that we're just on a flat plane and that we're actually doing Euclidean geometry. There might be a very subtle difference, almost unnoticeable to us, in terms of whether we're on a plane or on a sphere. But there's a natural series of questions here. What does this kind of geometry on a sphere actually look like? So the geometry looks close to Euclidean. We have notions of lines and points and circles. We can also talk about perpendicularity. But do we have, for example, orthocenters, circumcenters, circumcircles, midpoints, Pythagoras, all the many, many constructions of Euclidean geometry? Do they work on a sphere? It's a very natural and interesting question. So for example, in this picture here, this is illustrating, well, you have a sphere here, And then on the sphere, you have 3 points, and I've drawn parts of the great circle, so a little spherical triangle. And I've tried to find a midpoint of that side, midpoint of that side, a midpoint of that side. We have 3 midpoints. And then maybe here are the perpendicular bisectors. The question is, do they meet in the circumcenter? If so, is there then a circle that passes through the 3 points, which has this point as its center in some sense? So we can ask lots of questions about Euclidean geometry. How much of Euclidean geometry transfers to spherical geometry? And one question that we're going to have to wrestle with is, how are we going to measure things? What are we going to use to measure? Are we going to use angles and distances? Or are we going to use quadrances and spreads? Or something else? What is the best way of understanding measurement on the surface of the sphere? That turns out to be a very important but highly non-trivial question. And I have to say that probably most of the history of the subject has gone in a rather unfortunate direction when answering that question. We're going to be able to set things right and put things on the proper course here because we know about rational trigonometry and we know that it extends in a beautiful way to hyperbolic situation. We'll see that it also extends in a beautiful way to the spherical situation. So next time we're going to start addressing some of these questions. We're still going to stick with just a basic introduction. We'll talk a little bit about elementary geometry in the spherical case, and I'd like to introduce then this variant of spherical geometry called elliptic geometry. So I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.